quick introduction. My name is Axel Klenk. I'm working at the University Pompeu Fabra with Robert Castelo. And yes, that's the famous institute in Barcelona that is on the beach. I'm together with Robert working on GSVA, and Robert is one of the original authors of GSVA, and he's here in the room to support you if you have any problems with reproducing what we are trying to show. Anything else? This is using the development version of GSVA. So if you install the release version, it will not work. This is the current devil, and I suggest, are you finished with copying that? No. No. How do I scroll?
Probably lost the focus of the window. So, two fingers.
2 fingers. Perfect. I propose that you use these Docker containers that you can pull here if you're using Docker at all, because they will have the right environment and our version
Stickers for anyone.
to make things work. So today we'll have 3 parts. I'm showing you a very simple topic, how to import gene sets from GMT files into GSVA. Has anyone ever or everyone ever used GSVA? GSVA is a single sample gene set analysis package, and single sample here means that we do not have a comparison between different columns and get a p-value or anything as an endpoint of an analysis, but we transform the rows of our data matrix from genes to gene sets and can use the resulting matrix of gene sets as a starting point for further analysis, which is an important difference. So we look at now how to import GMT files, and then I'll show how, hopefully, how to analyze a bulk RNA seq dataset, and Robert will demonstrate the use with single cell RNA. So I'm just going to the RMD files that are the source of the vignettes that you can find on the other website. Does this have something like a pinch down? So, what are GMT files? GMT is the abbreviation for gene matrix transposed. It's a text-based format for storing and distributing gene sets. That was published together with a molecular signatures database, MSigDB, from the Broad Institute. Broadly, we have a gene set in one line that's tab delimited. The first column will be a gene set identifier. The second will be a short description. And then there's gene identifiers of the genes that make up the gene set. And of course, since every gene set has a different number of genes, this is not a perfect rectangular matrix. And cannot be read easily with read table or read CSV, and needs specific functions for reading it. There are already such functions in the package GSEA base. There's getGMT, and also in a package called QSH, there's a function readGMT. And I'll briefly show why we had the feeling that we need to add another one. In GSVA, there is now a package function readGMT. So how do we use that? Probably.
Apple, enter for one line.
For one line, Apple, enter. Perfect. So we are loading package GSVA base, and we are loading package GSVA. Input to our function readGMT is either URL or the name of the file of the GMT file. So we use the URL in this case. Let's see how the internet connection works and execute. Well, and that's it. And we see that the function readGMT returns by default, returns an object of class GeneSetCollection that is defined in package GSVA base, which is one reason why we had to load it. And we see that we have loaded around 5,000 gene sets in this time. And to get a quick view of this object, so we see some of the names, and we see that the gene identifiers used in this are UGO gene symbols. And you, oh God, how can I mark something? You will, do you see my cursor? Yeah. See that we have used this second argument, which says the gene ID type is simple identifier. This is adding some meta information to the GeneSetCollection object. So later on, other software will know this GeneSetCollection uses gene symbols. We will make use of this in the second part of the demonstration when we use automatic gene identifier mapping. So that's, I mean, it's as easy as that. We use readGMT, we get a GeneSetCollection back, and this can be used, for example, as input to the GSVA function. So that's not much about it. Then why did we add this function to GSVA when GSVA base already had a function readGMT? Now, the file format definition for GMT file says that the gene set names must be unique. We have, however, found GMT files that were distributed by Broad where this was not the case. And if you use their own no GSVA base, I think we're here. Function to read such a file that has non-unique gene set identifier, get GMT, will throw an error, which is correct behavior, but in some situations it's just not helpful to only get an error and be told something's wrong. So in contrast to that, we now have in our function readGMT, which is based on getGMT and just extended by two small features. Using the same file, what happens is there is a warning that something's not wrong. And then it says there are duplicated gene set names, and this has been resolved by using the method first. First means that it just retains the first of the duplicated gene sets and the others are simply dropped. It suggests, now let's see if I can do that. No. Let me look at the help page of readGMT. Oh, yeah, where it's perfect. Listing the available strategies for resolving this problem. So there's first, retain the first, there's drop all of them. There's union, combine of them. They have the same name anyway, so just make a unique set out of all of them. Keep the smallest, keep the largest, and so on. So you have the choice of a couple of strategies to resolve this issue, and you end up with an object afterwards that you can work with and not just an error message. Okay. Second new feature as I said, by default, we return this gene set collection because we think it's useful and it supports, for example, the automatic gene ID mapping if we need it. But some users may still prefer to just get back a list of character vectors containing the gene IDs. And for these users, we have built in an additional argument value type that can be set to list. And if you use readGMT with the same file, but with value list, you get the same warning because it's still the same file, but we see the returned class is a list now. Of course, there's no duplications. And if you look, it's a list of character vectors containing UGO gene symbols. So yeah, as simple as that. I think that's all I wanted to. Yeah.
Does it work for mouse genes, for instance, or here it's only?
Yes. At that level, it's really just strings. It gets more interesting when we try to do gene ID mapping later, and I think it would work there too, although we haven't tested that. But at that level, it's simply just text strings, and no matter what's in there. Any other questions on reading gene sets? Okay. I want to. No, I want to restart the R session to start from beginning.
To start from the beginning, but we need to do. You just go to this one, right? So,
yeah, but the R session is completely spoiled. So in session there must be restart R.
Okay, I mean session.
Yeah. Restart R.
Restart. Okay.
I would have said it's Control Shift F10, but.
But here, if you want to clear this, yes, Control L.
Yeah, exactly.
Yeah. So,
perfect.
You might want to maybe say this. I don't know. This. People. So if you go to the website, has a nice. If people wants to look at this.
Of course, if you want to look at the.
You have to go to this URL. So maybe functional dynamics of github.io/GSVA EuroBioC.
Yeah. But that's the one we used before, no?
Yeah.
Okay,
and then you can navigate to the vignettes.
If you want to see the result of executing the vignettes, they are here on the website already. But you can easily run the R&Ds yourself. It should.
If someone could just copy that link and put it into Slack, that we can, or
do that.
or even later. Yeah, I'm probably not going to do it now.
But what group of Slack? Is there a group for the conference? There's a group of the conference, right?
Yes.
Yeah.
Okay. So this is let me see.
Yeah. Someone's done it, so
It's already done. Okay, excellent. Okay, then it's done. Okay,
Let's do it.
excellent. Okay.
Okay.
Thanks.
Yeah.
Yeah.
So now we are looking at a real data set that's a bulk RNA-seq data set of whole blood taken from extremely early born babies. And this is published. You'll see the reference somewhere. And we'll start by importing the data from 2 CSV files, and the data is already pre-processed log CPM values. Here's the reference. Perfect. So again, we set the file name, that's trivial. Then we do a read CSV. As I said, that's just a comma-separated values text file. We have about 11,000 genes, and we have 21 samples. I think with an equal distribution of male and female neonates, and about half of them have been affected by a condition called fetal inflammatory response. before birth. And the research question is how this changes the expression profile after birth in whole blood. So, for example, yeah, so example of the data set. Next, the phenotype data that I just explained is in a much smaller data set that looks like this. And this is how the conditions are distributed. We have now read this in 2 data frames, and from these 2 data frames, we build a summarized experiment as an input to GSVA. So we load the library summarized experiment. We make sure that the column names and the row names of our 2 CSV files match, because otherwise there's a problem. And they do. And then we simply create a summarized experiment from these 2 and have a look at it. So nothing new about that. There's one special thing we need to do now, because now we want to perform the gene ID matching that I've already mentioned. And to do that, we again need to load library GSVA base and GSVA. And the only thing we need to do is call this function GSV annotation of this summarized experiment that we have just created. It's using Pompeu identifiers, and since it's human, we are using the human organism database. So we are again just setting metadata in this object for later gene ID mapping. We can have a brief look at the data. For example, by producing an MDS plot. Since I'm colorblind, I'll say on the right side, we have the ones that were not affected by FIR. On the left side, the ones that were affected. So that's nicely separated by the MDS plot. And the circles are the female neonates, and the squares are the male. So on the second component, this is also nicely separated. The information is there in this data set. That's for the expression data set. Next, we are going to import our gene sets. Exactly the way we have seen that before. This time, I'm going to use a local file and not download from the internet. Again, for the gene sets, these are using Google gene symbols. We need to set the gene ID type to symbol identifier. So gene sets, gene symbols, expression data set, entrées ID.
I have a question here.
Sure.
Is there any reason of why a log system was used for normalizing the state? Or?
Yeah, but this is part of the standard, let's say, Lima pipeline. We use Lima for analyzing. There is a publication, this data, and we use Lima. Lima is used. We use Lima Boom. You know, or you can use linear models, and you have your matrix of fluxity emission and expression, which are continuous, and you have your matrix of precision weights for the specificity, and then you can use linear models to analyze this data. It's quite a standard thing. instead of HR or TC2, and you could have similar results. I mean, this is but
Yeah, maybe for RNA-seq is okay, but for genomics.
but
maybe-
it's not proteomics. This
Yeah,
is
I'm just saying this just for RNA-seq. That was my question.
yeah, this is RNA-seq.
Because it's RNA-seq.
Yeah.
If there is any other data type, maybe this
We
normalization.
did proteomics. We did
With
proteomics.
the same normalization.
No, in proteomics we use proteomics specific methods.
Okay.
But sorry, is the normalization important at the end or?
So GSVA expects an input data that is normalized in the sense what you want to have for this kind of analysis that the samples are comparable, so that the technical differences are.
Okay, but it's not based on ranking.
We're not yet there. He's getting there. But if you can wrap up in a minute the next step of running GSVA, because then I want to have a couple of minutes to talk about single cell.
It will be, sorry,
He still has not run GSVA. He just
I'm
has
just
set up the whole
preparing that.
thing. The
So
metadata plays an important role. That's what he was saying about this symbol identifier. So we have gene sets with symbols, molecular data with entrées, and you will see later, I'll try to show you with ensembles, this typical thing that happens.
for the purpose of the presentation, we filter our gene sets down from roughly 5,000 to 150, just to make it run interactively. We run GSVA. We do that by creating a GSVA parameter object that receives as parameters a summarized experiment that we have created and the gene sets that we have created. We can specify the name of the assay because summarized experiments could contain more than one assays. So that's the parameter object that we have created, and all we need to do now to run GSVA is call the function GSVA using this parameter object as the only argument. And now it will map the identifiers from Uber gene samples to onto identifiers, which takes more time in this case than the actual analysis. And there we are.
This step is using the rankings and all this. Now, if you look at the dimension of this guy, has the same number of samples, but has the number of rows corresponding to the number of gene sets. So you went from genes by samples to gene set by samples.
Okay, my question was about the fact that the data was not normalized from the beginning. If the function works on ranking, is it really important? If you
Oh,
don't
why
work on
you
no
need the data
CPA or
normalized?
On raw data or on any way of.
You can try. You can try
Log
to
transformation maybe, but.
You
I don't
can
know if it was an example.
try to give data unnormalized, but I think that it makes more sense to be normalized.
Will give a higher percentage of false positive if you do not normalize.
There's no
If you-
positives and negatives here. We are just
No,
performing.
he speaks about
No,
downstream.
I'm saying that especially for the question of ranking, if you don't want to log two transform, you can maybe do just a quantile, which is already kind of based on ranks. And that will improve the GSVA output into our experience.
Not transformation shouldn't change the order of the view.
Exactly.
It should not.
That will
It
not
doesn't.
impact. So
No, no.
not the impact if you change the order of the view.
That's right.
No, but this log CPM data is using the Lima pipeline, so it's using TMN normalization, so they are adjusted for library size, let's say.
Well,
So which is one of the major factors that influence differences is the variable sequencing depth across libraries. And you want to have that, at least that kind of thing, sort of, right? The RNA composition. And that's why we suggest to give input as input normalized expression units to GSVA. It's not important whether it logs CPMs or log TPMs.
Or single
Proteomics data, we also can
There's next.
analyze. So maybe,
I want to ask the question. So you showed that using read GMT function, you
Yep.
can read gene set as list.
Yep.
So, what if you already have a list in that
You
format?
can use
You
it.
can convert it into gene set collection.
We don't do that conversion. Currently, there's no function for that. You can directly use such a list, or you can use a gene set collection. Both is possible, but gene ID conversion only works with gene set collections. That's fun.
Because it's something that
We have a lot of ideas for the development version, and
So maybe let's, for the sake of time, because we're running late and I think the single cell part is also interesting. Let me just wrap up this part very quickly and show you quickly the single cell part. So here, what Axel showed, initially at gene level, you have this nice separation between exposure to inflammation and sex. The gene sets that we're giving is the immunologic gene collection from ECDB, and we reduce it to those gene sets relevant to innate and immune and adaptive response, because that's play a role in this study. And when you do that, and then you do again now on these scores, you can simply do, you have this object ES, this, you give a summarized experiment in, you get a summarized experiment out, only that the assay, the units of expression are now pathway level units of expression. So you can do a plot MDS directly like that. And here you get still the same separation, but you don't get a separation anymore between sexes, because there is no sex-specific gene set in these gene sets that we give. The results that you're getting depends on the gene sets that you're giving. That's important to keep in mind. Play an important role. If your gene sets don't make any sense, your output is not going to make any sense. If your gene set doesn't have a sex-specific genes, you're not going to see a sex-specific effect. Okay. And then having that you can do a lemma pipeline, different expression analysis at pathway level. We don't need to put the sex as a covariate on the GSVA scores because sex has no effect. There are no relevant genes for that. And then you can use, so that we incorporate recently, there is this relationship that often happens between the precision of the gene set GSVA scores and the gene set size, which is usually larger gene sets have more precise scores, and you can use that exploit that in the lemma trend pipeline by calling, there is this function here, where I did it, here. When you call gene set sizes on the output of GSVA, it will give you the sizes of the gene sets in a vector, but not the original ones, the filtered ones, because not every gene set has a matching in your molecular data. Not every gene has a matching in molecular data. And this you can give directly this vector of sizes to the lemma trend pipeline here. Trend equals this, and then lemma will take it into account. This is an integration with our pipeline. And now going quickly to the single cell part.
Was that tested without trend? Lemma no trend.
Lemma no trend is when you don't use trend argument. When you don't use any lemma no trend, it's the classical lemma. And the difference is that, according to Gordon Smythe, the author, is that you increase a little bit the statistical power. Depends on the data. In this particular example, it's negligible. You gain two different express pathways or something like that. Now, the thing is that people started using this. So the packages originated more than 10 years ago, where there was no single cell data, but people started using it with single cell data, and of course it's very slow with single cell data, so we have to make a few adaptations for this. And we've been working on this, and there is a first implementation that this with single cell data that makes it performant. This is illustrated with this PBNC data on 4,340 cells. Here we show a classical pre-processing of the single cell data, where you remove low quality cells and lowly expressed genes. And you end up with a matrix of 8,000 genes times 4,000 cells. We compute library factors, normalize again the counts, you obtain some log quantity, but this is a sparse. So here you only have positive values, non-zero values, where you had a non-zero count. Okay? Everybody with me? So the matrix is sparse, so the whole matrix is big, the non-zero part is small or manageable, let's say. Okay? So we import again the gene sets, Here we're using a specific PBMC cell type gene set collection of just 22 gene sets. This was published, it's part of an earlier study of some other people. And then when we're going to run this, in this case, this PBMC data from 10x, the genes are ensemble genes, okay? But our gene sets are symbols. So what we do, we set up the annotation metadata on the single cell experiment object as ensemble identifier. And this name of the package is important because the package is the one who has the mapping, what ensemble is what symbol. And once you put this, when you call later GSVA, GSVA will take care of the mapping. The mapping is done in the direction of changing the genes in the gene set to the standard of the molecular data. The molecular data is untouched. You have the same number of rows. Why? Because changing the genes in the gene set is not dramatic. You have a gene set that grows by a gene or loses a gene, it's the same gene set, okay? Unless the gene set becomes null, but then you don't want to study it anymore anyway. Another thing that we have to do in this particular example, the data is stored as a HDF5 backend delayed matrix thingy, so it's on disk. We're working to have native support in that, but we're still not there. We have only support right now to something called DGC matrices, which are sparse matrices that take less space in memory. So we're doing this step here to coerce it to this type of matrix in the future, near future. Hopefully, next release we don't have to do this. And then you work the same way. You do the parameter object, the single cell experiment object, the gene sets that we just read. You have to say the assay, so you have to be aware where are the normalizations of expression. What's the name? In this case, it's log counts. And then you just call GSVA with the parameter object, and it will do the calculation. In this case, it took like 15 seconds for 4,000 cells, okay? Which with a classical algorithm, it would take, I don't know, quarter of an hour at least, okay? So this is here it's saying it's using something called a sparse algorithm. So the result is slightly different than the classical algorithm. You can get back to the classical algorithm by changing this sparse parameter from true to false, and then it will go into the classical regime. But the sparse algorithm is much faster in the things that it's doing, and I don't have time to explain the math behind it. But it works the same way with the bulk. Once you've done this, then you use the scores in the way you like. And here, typical thing is to say, well, I'm going to do some clustering using these scores. Now I don't have anymore 8,000 genes. I have 22 gene sets and my 4,000 cells. So I'm going to build a nearest neighbors graph using those GSVA scores. I'm not going to reduce the dimension with PCA for this purpose. Why? Because I've already done it. I've done kind of a supervised dimension reduction where I say, what are the dimensions I want to reduce to, which are sort of biological meaningful dimensions. So I'm doing that here. Then I'm clustering with some community detection algorithm. And I'm tuning this parameter to get the number of clusters that I should expect for PBMC data, which would be like about 5 cell types that are present there. You know, it's T cells, B cells, natural killer monocytes, and dendritic. And then I'm just going to annotate this cluster in a very simple way, which is I'm going to go through the matrix of GSVA scores, cell per cell, and say what gene set has the highest GSVA score. So that gene set is annotating this cell. And then I'm going to go through the clusters and say, what is the most frequent gene set in the cluster? And then I'll get this result here, okay? I'm not claiming it's entirely correct, but it's a way in which you're doing the things that you know what you're doing at each step, because you're doing things in a more supervised way. So that's everything I wanted to say about the single cell. There are other stuff that we haven't said. For the proteomics data, and seeing Laurent here, we had a feature request from a guy who said that he had so many missing values, whether the algorithm could run discarding them. So we implemented that, but not for this algorithm in particular, for another it's called SSGSVA, which is another that is also implemented. And we will port it to this other more complicated algorithm So in proteomics, this happens, and Clement was also saying the previous talk that that's the case when you have 80% of missing values, you don't want to impute.
Do you have any recommendation on what should be the minimum size of genes that
I would say, I mean, it's like imagine you're doing the arithmetic mean. You want to do an arithmetic mean on, let's say, 3 genes, because you have a standard deviation in a way, although it's not exactly doing the arithmetic mean. I'm not sure it makes a lot of sense to consider gene sets of less than 3. Maybe if you know what you're doing, maybe 2 or 1, it doesn't make any sense. So, yeah. And then another thing that is not here shown, but is coming on the way, is the support for special experiment objects, so that you can run the algorithm directly on a special experiment object, and it's the same thing. Parameter object, run GSVA, and just take the considerations specific for the data that you're getting, that you're analyzing, and that's it. Okay, I'm sorry that we couldn't do this in a more expanded way. Yeah.
Obviously, can be normalized, so does it have to be with a log CPM, or it can be any normalization in log scale? For example, R log from the result or something like that.
Yeah, exactly. Whatever that it makes the columns more or less comparable, that it sort of corrects the different sequencing depths of the samples, and any normalization should be. Before, in the previous versions, you had to be only aware whether the data that you were giving were continuous or discrete. And now in this new version, the algorithm is going to look at the data and decide by itself it's going to be discrete, because certain regimes, it uses a non-parametric estimation with Gaussian kernels or Poisson kernels, and now it's making this decision sort of automatic. Yeah.
If you had to compare with other methods such as AuCell, for instance, what would be the advantage of using GSVA or AuCell or?
Yeah. I mean, there are papers already doing benchmarking, and people who've published these more recent methods, they benchmark all of them against GSVA, and GSVA ranks very bad according to them. I mean, it's the typical thing in methods of paper, and well, GSVA wasn't designed for single cell. So I know that it has some caveats, but we are addressing them. So we have not benchmarked yet this version. This is really out of the oven, very hot, very warm still. But I think that the things that GSVA is doing make sense. The steps that it's doing to get the, so it's doing 2 steps. One is step in which you attempt to bring all the genes in a common scale of expression, and then you go on the columns to do the rankings, to do the enrichment per column, okay? And then in many algorithms, most algorithms don't do this first step. Many algorithms, the second step in different ways. You can do it in a competitive way with Komolov-Smirnov competitive random walks. You can do it in a parametric way. You can do it different ways. The package implements 4 different ways of doing this. One of our own algorithm, then there's GSVA, Plage, which is first principal component, the loadings, and the z-score method. But of course, then you have AuCell, I don't know. There is a plethora of algorithms for doing this. And yeah, I think you should try every of them and decide what makes what makes better. What I can tell you is that the paper that described this probably more than 10 years ago is going to probably go over 10,000 citations by the end of this year. So if so many people uses it, I guess that something good must be doing it. 10,000 citations is not a non-trivial number.
Is there a way the outliers are handled in the new version?
Yeah, well, at the moment in which you transform into ranks, okay, then the outliers are dumped in a way, you know. But internally, you end up working with ranks.
The outliers should be handled before ranks. Otherwise, they will dominate ranks.
I guess we can have this discussion maybe in the coffee break. But
yeah, in genes, if there's an outlier gene and you rank by expression, it will always be the top or the bottom.
So it will be number 1, and the second will be number 2. That's it, right? Yeah.
In single cell experiment, sorry, could you also implement this? That's also those EuroBioC based.
That will be like a process that you do before GSVA. You can do it outside GSVA. You can do your clustering. Actually, this publication I mentioned here is from 2019. Here, not going to find it now. Where was this? Here, yes. These people here, this publication, they did exactly that. They cluster, they did pseudobulk and then evaluate number of methods in pseudobulk. I don't know why they did exactly that. And actually in their benchmark, GSVA was the best performer. But this was, of course, 5 years ago.